Greetings, welcome to lecture number 37 on basic circuit theory. I am Razavi. Today we will continue to look at the response of RLC circuits and consider some topologies that are different from just simple series and parallel combinations. Again, our objective is to just get comfortable with writing equations and solving differential equations and that sort of thing. And in fact, we will see that there are some interesting cases, and for those cases we have to look at differential equations that have an impulse on their other side, on the right-hand side. So we'll talk about those. But before we go there, let's see what we covered last time. If you remember, we looked at this particular circuit, which is really a series RLC circuit, except that I have introduced this dependent current source from here to here. And this current source monitors the current through the inductor and multiplies it by K. So after we solved the circuit, we saw that the capacitance that appears in our differential equation is of this form, C divided by 1 minus K. And that tells us that equivalently, the capacitance is scaled by a factor of 1 over 1 minus K. That's an interesting property. We haven't seen this in typical RLC circuits, and this arises because we have this dependent current source. So in fact, this is something that we can use in practice. For example, if K is equal to 1, some interesting and weird things happen here, right? You see that if K equals to 1, we decided last time that because all of the current flows through the inductor and through this guy, no current can flow through the capacitor, so the capacitor voltage is always 0. From another perspective, we can say that with K equals 1, the equivalent or the apparent value of this whole structure looks like a capacitance that has an infinite value. Right? These two together act as a capacitor that has an infinite value, and when we have an infinite capacitance, we cannot create any voltage on it, we cannot create any charge on it, right? Any charge we put on the capacitor will not give us any voltage other than 0. So these are all interesting aspects of this circuit. Then we turned our attention to this one, which has a current source with a switch, and then this sort of combination here. And initially, the switch is off, it's open, so the current flows through the resistor and through the inductor. So that creates an initial condition in the inductor. And then at time 0, we close the switch or we turn it on. Now this current circulates in this loop, and it's isolated altogether. And then this circuit reduces to a parallel combination because the left terminal of R is also grounded. So this looks like a simple first parallel RLC combination, and it can be analyzed in the form that we did before. The only difference is previously we had assumed a finite initial condition on the capacitor and 0 in the inductor. Now it's the other way around. We have a certain current in the inductor, but a 0 volt difference across the inductor, across the capacitor. But the analysis is similar. The differential equation doesn't change, it's just that the initial conditions have changed. Okay, so today we will pick up another example that we started last time, but before we go there, I need to talk about differential equations that have an impulse on the right-hand side. These are a little tricky, so we have to deal with them specifically and see how we go about solving these equations. Differential equations with impulses. Okay, so suppose I am given a differential equation of this form. For example, alpha d squared y over dt squared plus beta dy over dt plus gamma y is equal to delta of t. Okay? This is a differential equation that I'm given, and I'm asked to solve this differential equation. All right? And I also need two initial conditions. So let's worry about those a little later. Okay, so how do I go about solving this differential equation. There are different methods. If you know the Laplace transform, that's the easiest way actually. But if you don't, we can still solve it. So here's the procedure for solving the circuit. We're solving the differential equation. So our procedure for solving this equation goes as follows. Step number one, we change the right-hand side from an impulse to a step. So change, or maybe I should say replace. So replace impulse with a step. Okay? And create a new differential equation. All right, so to avoid confusion, I will not call this y anymore once this is u. I'll call it something else. So here's the new differential equation I have created. It has the same coefficients, so alpha d squared z over dt squared plus beta dz over dt plus gamma z is equal to u of t. All right, so I took the original equation, I replaced the impulse with a step, and I also called the unknown, the function z, instead of y. All right, so we have this new equation. Now we can solve this equation. This equation typically can be solved more easily than this one. For example, we know that for a second order system, we have these types of responses, right? So I know that z must satisfy one of these three, depending on the relationship between alpha and beta and gamma, depending on the roots of that second order polynomial that we have seen in the past. Okay, so the idea here is that I will go and find z from this equation, right? That's not that hard. So I will write, for example, if I know from alpha, beta, and gamma that it's an overdamped system. So if it's overdamped, I'm going to write z of t is equal to, from here, right? So I have a1 e to the s1t plus a2 e to the s2t. No, it's a simple second order differential equation. I know there are three possibilities, so here's one possibility. But is that quite correct? Not quite. Let's think about what happens to z at time infinity. At time infinity, these are 0 because we know that these exponentials decay for our RLC circuits. So, but this equation does not necessarily say that. So at time infinity, z of t is presumably constant. If it's constant, this derivative is 0. This derivative is 0. So z is equal to 1 divided by gamma. And that's not 0, right? So what we know is that z at time infinity is equal to 1 over gamma. At time infinity, this side is just 1. These two derivatives are 0 because z is constant. So z has to be 1 over gamma, and that's not 0. So this says it has to be 0. This says it should not be 0. So then what are we going to do? It's very simple. We just add 1 over gamma right here. So our expectation is that this overall solution satisfies this differential equation. All right? Okay. So we have found z of t in terms of S1 and S2, which are obtained from the polynomial here, and in terms of this 1 over gamma, which comes to give us the value at time infinity. Of course, for the other ones, the same, right? We just add plus 1 over gamma to these to make up for that final amount. All right, so I have found z of t, but I'm really looking for y of t, right? So what do I do? Okay, so in the third step, we say differentiate z of t with respect to time. So the idea is that, in a sense, this was the response to a step. I want the response to an impulse. So if I have the response to a step, I can just differentiate it to find the response to the impulse. This is something you might have seen in linear systems and so on. We won't bother with the details, but here's the procedure. So we're going to take the derivative of this, right? So we say dz over dt is equal to a1 s1 e to the s1t plus a2 s2 e to the s2t. All right, you see that this 1 over gamma doesn't really play a role anyway because we're differentiating it. Nevertheless, just to be careful, we write that there. Okay, so this is the derivative of z. And now I will say that the y that I was looking for here is in fact this one. So I say this is equal to y of t. Okay? All right. So, in summary, what we do is if we are facing an equation like this, let's say we have solved the circuit and this is what we get, then one possibility of solving this equation is to say, create a new equation where this is u and this is something called z. Solve for z. We can find z using these forms. Then differentiate z to find y. So that is our equation for y. Okay, so one last point. How do I find a1 and a2? Okay, so here's the key point. A1 and A2 should be found after we differentiate and after we find y. Because we already have initial conditions for this equation, right? So this equation came with some initial conditions. So let's say it came with something like this. So y of 0 is some amount, so let's call that k1. And y prime of 0 is some amount, so we'll call that k2. Right? Any second order differential equation must come with two initial conditions. So now we go ahead and satisfy these. So we say at time 0, we should have a y of 0 is equal to k1. And then also y prime of 0 should be equal to k2. So y of 0 means evaluate this at time 0. And y prime of 0 means take the derivative of this and evaluate it at time 0 and equate to k2. So with these two equations and these two unknowns, we can find a1 and a2. All right, so that's the general procedure for solving an equation of this form. So it's important to remember that these initial conditions are enforced after we found y, not for z. Okay, for z you cannot apply the same initial conditions because these relate to y, not to z. All right, so first we find the general form of z, and then we say that's y, then we enforce the initial conditions. Now we have a1 and a2, we're done. Okay, now with that we can go back to one of the problems that we studied last time, which was sort of interesting, and let's look at that. So here's an example of what we covered last time. We had a step as usual, so V1 u of t, and this step was applied to a resistor R, an inductor L, and a capacitor C. And we were interested in this voltage here, which we call V out, as a function of time. Okay? All right, and then our assumption is that the inductor and the capacitor have zero initial conditions. So we just apply a step here, it jumps from V1, 0 to V1, and then drives the circuit. Now we try to predict V out just qualitatively, and its behavior as a function of time. So if you remember, we said that V out should go like this, right? So V out starts from 0 because the capacitor has a 0 initial condition, and then ends in 0 because this inductor at time infinity becomes a short circuit. So our guess was that V out would do something like this. Of course, it could ring for a while before it settles, or it could go just like that. All right, but now we want to actually find the equation for V out. Okay, so no problem. We go ahead and write a KCL probably at the output node as we do usually and see what we get. All right, so I have the current through the capacitor. That's just C dV over dt. I need the current through the inductor as well. How much is that? If you have the voltage across an inductor, V out, then the current is just 1 over inductance integral of V out with respect to time. So I can write that, and then these two flow through the resistor and give me a voltage. So we write a KCL here, we write a KVL here, we're done. Okay, so let's write the currents. We have a current through the capacitor. So that current is given by C dV out over dt. We have a current through the inductor. That current is given by 1 over L integral of the voltage across the inductor, which happens to be V out dt. These two currents add up and flow through the resistor to give us a voltage drop. The voltage drop from here to here will be given by this resistor times the current through it. So that voltage drop is R times 1 over L integral of V out dt plus C dV out over dt. That's the voltage drop across the resistor, right? Okay, now we are ready to write a KVL. We say this voltage is equal to this voltage plus this voltage. This voltage we found. This voltage is V out. So we add them together, and that should be equal to the input voltage, V1 U of t. Okay, so this is the equation governing the behavior of the circuit as far as V out is concerned. All right, so we got to go ahead and differentiate both sides because we have this integral here, right? So that's a fact of life. We have to live with it. So let's go ahead and do that. So we say we have R. I'm going to write this one first because this will be the second derivative. So we have RC d squared V out over dt squared plus then this one. So we have dV out over dt, and then finally we have this one R over L times V out, R over L times V out. This is the derivative of the left-hand side of the equation. For the right-hand side, what do we get? Well, we have V1, and then the derivative of the step is an impulse. So that would be V1 delta of t. So that's the equation that emerges from the circuit. This is the differential equation governing the behavior. All right, so we have an impulse on that side. It's annoying, but we have to live with it, right? So one possibility is to do this, right? So what we're going to say is we create a new differential equation, and to avoid confusion, we won't call that function V out anymore. We'll call it something else, Z. So we create a new equation. Let me go and change the color here. So we say RC d squared Z over dt squared plus dz over dt plus R over L Z is equal to V1 U of t. Okay, you're following that? So remember what we said. We said if you have an impulse, first change that impulse to a step, and then write a new equation and call that Z, not Y anymore. So that's what I did. I had an impulse, I changed it to a step, U, and I changed this from V out to Z to avoid confusion. Okay, now I have this. What's the expression for Z? Same as before, right? We said that the expression for Z would be one of these three plus 1 over gamma. How much is 1 over gamma? Gamma is the ratio, when these go to 0, is 1 over this. So here, when at time infinity, these go to 0, the value of Z will be V1 over R over L. So we say Z at time infinity is equal to V1 over R times L. So for example, if you are dealing with an overdamped response, I can say that the Z of t is equal to A1 e to the S1t plus A2 e to the S2t plus the value at infinity, V1 L over R. Okay, so that's Z of t. All right, now we go ahead and differentiate this to find V out of t, right? Because that's what we decide to do. We differentiate. So let's go ahead and differentiate this. So we say dz over dt, which is the output voltage we are looking for, is equal to S1 A1 e to the S1t plus S2 A2 e to the S2t, and then this goes to 0, so we're done with that. Okay, so this is the form of V out for that circuit. All right, that's the form. And now we just have to find A1 and A2 for this V out expression. How do we find A1 and A2? We have to find the initial conditions for the circuit and then use those initial conditions to find A1 and A2. So let's go ahead and find the initial conditions. So find initial conditions. Okay, so the first initial condition is that V out at time 0 plus is 0. Why? Because the capacitor wants to hold that voltage at 0. All right, so we have V out at 0 plus is equal to 0. All right, that's great. Okay, but we need one more initial condition, and it has to be in terms of V out. Now, what we do know is that the current through the inductor is 0 at 0 plus. But somehow we have to translate that to something in terms of V out. Okay, so what I know is that this current is 0 at time 0 plus. And what that means is that this current plus this current should be equal to this current at any time. So let's draw the circuit at time 0 plus. So we see that this side is V1 because it jumped to a step of V1. Then we have this resistor. This inductor is open, so we just throw it away. We don't worry about it. And we have the capacitor like this. And what we know is that this current can be obtained as how much? We have V1 on this side. We have 0 on this side because the capacitor is maintaining a 0. So it's V1 over R. So this current is V1 over R. This is only at time 0 plus. So the current to the capacitor at time 0 plus is V1 over R. Right? That makes sense because at time 0 plus this is open, this has jumped, this is 0, a current flows this way, so it's flowing through the capacitor. And I know that the current through the capacitor is given by C dV over dt. So I can say C dV out over dt at time 0 plus is equal to this value, V1 over R. So that's the second initial condition I was looking for. With these two, I can find A1 and A2. And then we are done. Okay, so there's another point that we have to keep in mind both here and here when we're following this procedure for computing. First is Z and then V out. And it's as follows. So we decided that we have a differential equation and there's a step on this side. This is the new differential equation I created. So presumably Z is 0 before time 0, right? Before time 0 there's nothing, and it's only after time 0 that we have applied a step. So that means that I have to multiply this result by a step. u of t. Not this one, this one. Z of t has to be multiplied by u of t. Right? Because z of t is 0 before time 0, and then after that, in response to this step, is doing something, right? It does generates an output. Okay, so now when I go and differentiate with respect to time, something interesting is happening. So I got the derivative of this times u of t, so that's what I found here. We're good with that. But then we also have the derivative of this times this whole thing. All right, so here we just have to be careful. The derivative will be an impulse, but that impulse will be available here only if its weight is not 0. And to find the weight of that impulse, we have to look at time 0. So that would be an impulse. And then what is the weight of this at time 0? At time 0, we would have A1 plus A2 plus V1 L over R, right? So if that value is 0, then we have no impulse. If that value is not 0, then we have an impulse. So that depends on the situation. In this circuit, that value would be 0, so we don't have an impulse on this side, and V out is free of an impulse. After all, that's what we saw, right? V out doesn't have an impulse. It cannot produce an impulse because we don't have any mechanism for that. So that's something that we always have to keep in mind when we are solving these circuits. Okay, so with these two initial conditions, I can find A1 and A2, and then I'm done. I have V out as a function of time. All right. Now, for some circuits, there's another approach that doesn't have to deal with this type of situation. So we can try to solve the circuit differently. And here's the idea. You see what happened here. When I wrote this equation, I had an integral here. And to get rid of that integral, I differentiated, and that's why I ended up with an impulse. So if I don't want an impulse, if I don't want to deal with an impulse, there's another way. Can I consider some other quantity in the circuit that does not give rise to an integral after we solve the equations? Maybe that's possible, maybe that's not. But that's something we can consider. So let me talk about the second approach so that you can see how that comes about. So we're going to call this approach, let's say alternative approach, alternative approach. So we look for a quantity whose equation does not have an integral in it. Then I don't have to differentiate, so I don't end up with an impulse. So maybe that's possible. So let's go here and look at the current of the inductor as one candidate for that. So I'm going to call this IL1, and I will pretend that IL1 is the quantity of interest here, not V out. If I find IL1 as a function of time, then it's not that hard to find V out because V is just L di over dt, right? So we start from here. And we ask, can we solve the circuit in terms of IL1? Okay, sure, it should be possible. So, because this current is called IL1, this voltage will be L IL1 over dt. So I'm going to write that voltage as L dIL1 over dt. This is the voltage across the inductor. So I'm avoiding the term V out because right now I am ignoring it. I'm just interested in IL1. So this voltage is equal to L di over dt. Now this voltage happens to be the capacitor voltage. So if I have the capacitor voltage, can I find this current? Sure, C dV over dt. So we're going to write the current through the capacitor is C. Well, actually, I write it right here. The current through the capacitor is C d over dt of the voltage across it. This is the voltage of the inductor and the voltage of the capacitor. We differentiate, multiply by C. That is the current through the capacitor right here. Okay. All right. Now, the two currents through the inductor and the capacitor add up and flow through the resistor. So that plus IL1, so this plus this flow through R. So multiply that by R. This is the voltage across the resistor. I added the two currents. I let the result flow through the resistor. I generate a voltage. So I can write a KVL. I can say this voltage is equal to this voltage plus this voltage, right? So this voltage is this plus this voltage. How much is it? LdI over dt. Okay, not V out, LdI over dt. So LdI1 over dt is equal to V1 U of t, the input, right? So we have obtained a new equation for the circuit that is only in terms of IL1. And fortunately, it doesn't have any integrals in it. So all we need to do is group things, and this will give us a second order term, this will give us a first order term, and this will give us the function itself. So it's a simple second order equation with a step on that side. So this equation will also have these solutions, except that we have to remember, because the other side is V1 at time infinity, we have to add something here, right? So let me just try to predict that. So I'm going to write IL1 is equal to A1 e to the S1t plus A2 e to the S2t plus something, right? At time infinity, IL1 is not 0. We know that here too, right? Because you see that at time infinity, this is a short circuit, so all this current is flowing this way. So we have a current of V1 over R through the inductor at time infinity. So that should be V1 over R right here. So that would be this term. At time infinity, this derivative is 0. This derivative is 0. So IL1 is equal to V1 over R. So that's the expression that we would have. Or we would have this plus V1 over R, or this plus V1 over R. That is the expression for the current of the inductor. Okay. So now we can solve the circuit. We can find A1 and A2 if we have the initial conditions for IL1. And we have those initial conditions, right? So the first thing is that we know IL1 at time 0 plus is 0, because the inductor doesn't want to change its current. We've seen this before. And then we also need one more condition in terms of IL1. So previously we tried to recast that in terms of V out. Now we have to express in terms of IL1. All right, this is a little tricky, so stay with me. All right, so I need one more equation for the initial conditions. What I can say is the following. Let's look at time 0 plus. So we say at t equals 0 plus. We see what's going on here. At time 0 plus, we have LdI over dt. LdI over dt is this voltage, right? And just happens to be the voltage on the capacitor. So LdI over dt at time 0 plus is 0 because the capacitor wants to force it to be 0. So we say LdIL1 over dt is equal to 0, and that means that dIL1 over dt at time 0 plus is 0. All right, so we have this equation, this initial condition, and this initial condition. So we can find A1 and A2. So that completes the solution. All right, so this method avoids having an impulse on the other side. It finds IL1 first, and now if I want to find V out, I just say LdI over dt is V out, and we can find that as well. All right, so these are different ways of solving these problems. But it's good to know this, and it's good to know that. Each of them has its own benefits depending on the problem that we are facing. Okay, so with that, we are ready to look at one more example today. So let's go to the next page and consider another example here. Okay. So this time again I have a step. So V1 U of t, and I have just a series combination of devices in this form. So I have a capacitor, an inductor, and a resistor, LR, and I am interested in this voltage. Now you may say, we analyzed this before because we did look at a series RLC circuit before with a step input. Yes, but previously what we were looking for was not the voltage across the resistor, it was the voltage across the capacitor. So you can go back to that circuit, and however we solved it, from that solution we can readily find the voltage across the resistor, or we can just solve it completely fresh and say, okay, I'm given this circuit, I want to find this voltage, let's see what we can do, right? Yeah, either one is fine. Okay, so the initial conditions on the capacitor and the inductor are 0, so we just proceed as usual. All right, so what we know is that the current to this resistor is V out over R. This current flows through the inductor and gives us a voltage. So we have a voltage here, and that voltage is given by, I write down here, is L di over dt. So L d over dt of V out over R. And this current, whatever it is, also flows this way. So that's the voltage across the inductors. You also need the voltage across the cap because I'm trying to write a KVL. So the voltage across the cap, we know, is given by 1 over C integral of the current through it. The current through it is V out over R. V out over R dt. Okay, so we have this voltage, we have this voltage, and we have this voltage. We add them up, equate the result to this input. So we see that I have 1 over C integral of V out over R dt plus L d V out over dt. There's a factor of 1 over R here. And then finally plus V out. This voltage plus this voltage plus that voltage must be equal to this voltage, V1 U of t. All right. Okay, so that's the overall equation for V out. Again, the problem is that I have an integral on the left side, I differentiate, and as a result, I end up with an impulse on the right side. So that's the fact of life that we have to live with. Okay, so let's go ahead and do that. This becomes a second derivative, so we have L over R d squared V out over dt squared plus the derivative of this guy, dV out over dt, and the derivative of this guy plus 1 over RC V out is equal to V1, derivative of the step, an impulse. All right, so similar to what we saw before. Okay, all right, so we have this. Now, before we jump into more details, let's try to sketch V out as a function of time, just to get a feel for what it looks like, right? All right, so let's do that. I'm going to try to maybe draw it over here. So V out as a function of time. Okay, so before time 0, V out is 0. Why? Because there was nothing here, right? This was 0, and all of these initial conditions were 0, so there was nothing at the output. So V out is 0. Okay, now the question is, how much is V out at time 0 plus? And that's a very interesting and tricky situation. So what can I say here? I'll give you 1 minute to think about it. It's the quiz of the day. Okay, so how much is V out at time 0 plus? Well, what we know is that this voltage is given by the current through the resistor times the resistor. And we know that this current has to come from the inductor. And the inductor current is 0. That cannot change suddenly because we don't have any infinite voltage available. So because the current of the inductor is 0 at 0 plus, the output voltage is also 0 at 0 plus. Okay, so that's fine. And then how about time infinity? What can we say about that? Well, at time infinity, assuming that nothing is changing because the input is constant, then the capacitor has a voltage that's constant with time, whatever that might be. That means that the current to the capacitor is 0 at time infinity. If the current to the capacitor is 0, then the current to the resistor is 0, which means the output is also 0. So this has to go like that, back to 0. And again, depending on the dynamics of the circuit, it might go like this, or it might just go like that. So that's the overall picture that we have of V out before we go and try to derive it. Okay, very good. Let's go ahead and write a new equation based on our procedure. So our new equation would be of this form. It will be L over R d squared z over dt squared plus dz over dt plus 1 over RC z is equal to V1 u of t. All right? So that's V1 u of t. That was the procedure, right? We changed this to u, we changed this from V out to z just to avoid confusion. And now I can find an expression for z, just like before, just like the previous problem, right? Depending on whether it's overdamped, critically damped, or underdamped. The only thing is that I have to remember that z at time infinity is not 0, it's V1 times RC, right? So we can write that. So for example, z of t is equal to a1 e to the s1t plus a2 e to the s2t plus V1 times RC. At time infinity, these are 0. Z of t is equal to V1 over RC. And that's true because these are 0. Z is equal to V1 times RC. Okay? And then we differentiate this to find V out. So we say V out is equal to A1 S1 e to the S1t plus A2 S2 e to the S2t. All right? And we now have to enforce the initial conditions to find A1 and A2. The initial conditions are as follows. So we know that V out at time 0 plus is 0, right? So that's one initial condition that we have. V out at time 0 plus is 0. What else do we need? We need maybe derivative of V out at time 0 plus. So that's a little trickier. So we have to go back here and understand how much the voltage across the inductor is at time 0 plus. How much is that voltage? So at time 0 plus, this voltage is 0, the capacitor voltage. This voltage is 0, as we decided. So how much is this voltage? Is V1. So we say VL1 is equal to V1 at 0 plus. And from here, you can manipulate it to find an equation for V out once you consider that the current through this output is V out over R. I'll leave that as an exercise for you, and I will see you next time.